Hello, everyone. Welcome to CTF Radio. We are now on, we're just going to call it Season 3. Apparently, that'll be every year where we end up releasing episodes. We will increment the season number.
It's Season 4, man.
You're not even going to let me introduce you before I, Yeah, hi. So I'm Adam D, and then I'm super happy to have with me the great Zardus.
Hello, hackers.
All right, there we go. So you know us. We're here on CTF Radio, and what we wanted to talk about now, so we're sitting here about a month-ish until DEF CON, and Jan said to me, Adam, the Team Shellfish has probably been playing CTS, but we wouldn't know because we haven't really been playing CTS with them. But the one thing we do know that Team Shellfish is doing is participating in the AI Cyber Challenge. So he said, let's talk to the teams doing the AI Cyber Challenge. And I said, that's great, Jan, because as you may remember, we did an episode about that. That was Season 2, was basically preparing for that. And then actually from DEF CON, our AIxCC. So we're going to kick off the first of hopefully all of the 7 teams that are playing in finals. We don't know. We have to reach out to people. We haven't even done that yet at the time of recording, but
we got people on it. We got our best people.
You're just looking at me. It's going to be me. That's who's going to do it.
We got our best person on the job.
Who's definitely going to drop the ball. But anyways, I will definitely try my best to do that. And if you're listening to this and we haven't reached out to you, you feel free to reach out to us. We'd love to talk with you. So we're starting it off at home. Jan, why don't you introduce our 2 guests?
2 guests today need no introduction, but we'll give them one anyways. I'm going to kind of do my typical, rewind back to the start of the universe, right? There was the Big Bang and et cetera.
I can't rewind that far. I was trying to do a rewind sound effect, but I can't do it long enough to go back to the Big Bang.
Exactly. Eventually, humanity evolved to create capture the flag competitions, which, of course, as we know from this podcast, are the pinnacle of human achievement. And eventually, the CTF community evolved to create the pinnacle of badass CTF players, which is Shellfish. And eventually, Shellfish evolved to have multiple generations of hackers. And this is something that isn't unheard of in CTF, of course. You have multiple generations of a team.
But the way you're saying this makes it sound like Shellfish itself begets other Shellfish members somehow.
Yeah, that is a little weird. But, academically, let's say it's true.
Ah, okay. That tracks.
Yeah. So there's these multiple generations of mentorship in Shellfish. And if you go back to Season 1, I don't remember which episode, but we did an episode with several generations of Shellfish discussing this cool phenomenon. There's a number of CTF teams that are multi-generational, none as multi-generational as Shellfish, just due to raw passage of time. And I was in generation 3 of Shellfish when I was the Shellfish captain for a while, etc. And then I passed the baton to generation 4, which passed the baton to generation 5, which is crazy enough to when the AIxCC, the AI Cyber Challenge, was announced, they said, yeah, why not? Let's put our entire lives on hold and do this for a couple of years and see if we can change the world. So today we have 2 incredible Shellfishes who are the captains of Shellfish's AIxCC effort. And we got Clasm and Honolulu, aka Will and Lucas. Guys, why don't you emerge? Boom.
Guys, I think they're after me.
I've been here the whole time.
Wait, I think I have a clapping sound effect. Wait, how do I do this? Boom.
What's going on? Where's everyone?
Wow. Okay. So yeah, 2 years trapped in a room creating a cyber reasoning system does something to a person. That's what you can tell from Lucas. So this is great. So, okay. So now we have the 2 Shellfish AIxCC captains. Is that appropriate titles for you 2?
Yeah, let's go with that.
All right, great. So then, all right, Lucas, kick us off. Start us. I know we talked about AIxCC probably a year ago on this podcast. Can you tell
Do you remember
people...
we were sober on that one? Because I don't remember what we talked about, but it was a while
just
ago.
came from the dinner, I think. No, we went to the dinner.
We were
after.
going to the dinner.
We were going to the dinner
to
after.
the dinner.
So I think
So
we were
probably
probably still
sober.
sober.
We were in Las
But
Vegas. I think the answer was no.
we had just found out that we qualified.
No, that was a pre. We did the pre
Yeah.
interview.
Oh, and then
And
we
then
added
I
the
added
thing
the
to
thing
that.
at the end.
Basically,
Yes,
us screaming like crazy people.
exactly. I did way
Yeah.
more editing than I will ever do in any other podcast, but it was fun. Okay, so Lucas, remind us, what is the AI Cyber Challenge?
Sure. Yeah, I mean, so the AI Cyber Challenge was, I think, like August 2023 announced. And the idea was kind of, in a way, very simple, but also incredibly complicated. The idea was, at the time, we had just started the hype cycle of AI and GPT and all of these LLM things. And the question kind of arose, the natural question is, how can we use all of this for security? Because, I mean, over the years, we've seen various applications of machine learning and AI in security, but I think we can all agree that there was never really this moment where anyone actually believed that that would work. And all of the approaches that people had done were
In what domain? Because I
of
think
questionable usability.
Yeah, maybe
Right.
people at home, I think like, well, I don't know, Gmail's pretty freaking good at getting spam
Mhm.
email out of and since you're in the whatever this 5th generation that Jan talked about, I remember the days of having a Hotmail account and having no spam filter and having all types of messages go through. So, I think like
Yeah,
so maybe like
that's
what
fair.
area of cybersecurity were you not seeing the ML and AI applications of?
Yeah, I mean, I think we both me and Will kind of come from the background of binary and program analysis in general, aka trying to automatically find security vulnerabilities in programs. So trying to find these bugs that can take down entire machines or that can allow you to take over that machine, and these like really security critical bugs, and that entire field has kind of traditionally been dominated by tools like fuzzing, where you just repeatedly mutate and throw new inputs at the program until it eventually breaks. Where you're kind of like brute force breaking the software by just trying so many different combinations that it never expected. That eventually you find something that breaks, and then that's great. That's what you were looking for. And we had these tools and techniques before that were trying to find these things, and people had tried to use this machine learning approach of trying to mine data from existing software, trying to mine data from existing vulnerabilities. But I don't think anyone's seen any like super convincing arguments of like, hey, there's something here with this machine learning stuff that can really work.
And especially at the time, I mean, I've seen papers, like research papers that came out. I reviewed research papers at the time, and it was always like, okay, you're using like machine learning in some sense, but like the features that you're using, are they actually capturing what is the nature of that type of vulnerability? Like, are you just finding minor code clone differences that really aren't going to generalize to when you throw it against something like Windows or Linux?
Yeah.
I think.
I
Go.
was just going to say, I think that prior to AICC and really the introduction of LLMs into the greater society, a lot of the papers or research we were seeing being done were these AI or models that were trying to look for specific features or maybe classification of here's a function, is this function vulnerable? And it would spit you out just a yes or no answer. And these things were rife with like data set problems, inaccuracies, or what you were saying, Adam, is they were just identifying these things that they've seen before, the code.
Yeah, and I think a lot of the times, even when there were advantages, it seemed like they were mostly marginal and not really anything life-changing. And so just kind of to go back to the challenge, right, with these LLMs, where I think most of the research community, us specifically too, right, was like, hey, this actually seems like there's something here that might be useful. These models have seen so much data, they've seen so much software that it's almost impossible for them to not have learned anything interesting that we might be able to mine. And clearly the folks at DARPA felt the same. And that's kind of where the AI Cyber Challenge started. The idea was really, let's use these LLMs, let's fund people, let's fund teams to use these LLMs to the extent that they can, right? Like, let's make sure we really mine out the possibilities that we can do and build the best system to find these kind of like critical bugs with the help of these LLMs.
Awesome. And then this is also in the context of, Jan, can you describe just very briefly, like the previous Cyber Grand Challenge? Like, I want to make sure people understand the context here of what came before and what DARPA was and is trying to achieve with the AI Cyber Challenge.
Yeah, this is a great piece of context.
You're welcome. This is my job as host.
There you go. DARPA is no stranger to these sort of exploratory contests, right? 10 years ago, and that wasn't even the first contest DARPA ran. In fact, if we go back to even earlier contests in this kind of related in the tech space, and DARPA ran these self-driving car contests, which have, a decade and a half later resulted in, Waymos driving in the streets and people not needing to be driven or to drive their cars. 10 years ago, roughly, DARPA created the Cyber Grand Challenge. The idea being that there are all these techniques, algorithmic techniques at the time that were being created to find vulnerabilities, reason about their exploitability, and a little bit to fix these vulnerabilities automatically. And DARPA wanted to both understand the actual state of these techniques, their actual usability, because that can be hard to understand when reading academic papers on the topic, and also to catalyze more development. They created, to do this, the DARPA Cyber Grand Challenge, the CGC, and the CGC had this goal of basically pushing forward the creation of cyber reasoning systems, autonomous computing platforms that could analyze code, find vulnerabilities, fix them without any human involvement, just to see what is possible. Then, of course, after the CGC, all of these techniques that were developed for the CGC were augmented, continued to be developed, productized, got humans put back in the loop, because in the real world, you can, of course, have some human effort. It's all good. And really advanced the state of cybersecurity, and really set the stage for then a decade later, the AI Cyber Challenge.
Excellent. All right. Thanks, Jan. And then, so Will, talk to us about the one thing that everyone cares about: cash money. Money, money, money.
That's there was a lot of money online for AICC. I think it was 27.5 million in total.
Got to get that half.
Gotta get the half. I mean, I'm not missing out on $500,000. I don't know about you. I'll take it if you're leaving it on the table.
All right, great. So yeah, go ahead.
Yeah, but so in the lead up to the competition, all the teams that were competing were after the $2 million semifinals prize, which is, if you make it into the top 7 teams, you win $2 million. It's as simple as that. One of the things that we actually managed to also win on top of this was the small business prize. We wrote a very nice proposal, and the top 7 best proposals also won an additional $1 million in the lead up, which certainly helped fund our activities trying to get into the top 7 teams.
Are you saying that this effort needed a lot of money? He says, hinting at where we'll go later.
It's an expensive process. LLMs, not the cheapest things. Unfortunately, they don't run on dust and air. They use the liquid gold.
All right. So what's up for
Fish
grabs in
also,
August? So what for this finals? So we're in the AICC finals that are happening in August. What's the prize pool that teams are competing for? There's 7 teams left.
7 teams left. Top 3 take home some nice prizes, with third place at 1.5. That's where your $500,000 comes from. Second place at 3 million, and then first place gets $4 million.
Whoo, pretty nice.
In the Cyber Grand Challenge, 10 years ago.
Wait, you have to start your sentence by saying, back in my day.
In my day, for those that don't know, Shellfish also participated in the Cyber Grand Challenge. We got third place there. The prize was $750,000. So that prize is doubled for third place. Why do you think the prizes are like doubled?
Great question.
So, I mean, honestly, AICC seems to have a much more immediate, real impact, I think, than CGC.
Wow.
Not
Shots fired.
in CGC's, yeah, shots fired. But to be honest, the CGC programs were, custom written, 7 syscalls per program. Not to say that it wasn't like incredibly novel. I mean, for God's sakes, anger was born out of the thing, right? Was an incredibly like difficult challenge at the time without LLMs. But now that we have all of what's happened in program analysis from 2015 to now, plus this introduction of LLMs that help lift the human aspect out of it, we're working on software that's used in production by millions, if not hundreds of millions of people and companies every day.
Yeah, so the previous competition was crap, and the new one is good.
I'm glad. Yes,
but
exactly.
You missed the real answer, Will.
Inflation.
Inflation, dog. Yes, exactly, Lucas.
Ooh. Well, inflation only covers so
750K
much.
doesn't get you crap anymore, man. You got to get those millies.
That's
I think
true.
it's possible that there's 750K for AI and 750K for security.
Mm.
That's why.
Merging the two. I love it. I love it.
But kind of pulling this thread a bit, right? So the cybercrime challenge, you mentioned the whole way that it was run, the challenge problems that these autonomous cyber reasoning systems had to analyze, they were custom built and very simple in their interaction with the operating system, with their environment. Why do you think that is? Now, as you mentioned, AICC is a different beast. The challenges that you have to analyze and find, that your CRS has to analyze and find bugs in, they're full real programs on the size of web servers and stuff. How was that shift possible? Why did the CGC start small, and why did AICC go large?
I mean, I think there's 2 parts to it. I think the first part that you'll kind of have to think about too is, if you think about the space of the things being analyzed in program analysis at the time, it's not super surprising because, I mean, most of the modern techniques that we use today, right, like most of the fuzzers were barely in their infancy at the time. I mean, I think, like, yes, some people had been fuzzing since 2007, but really the fuzzing that everyone was doing with just simplest AFL with none of the modern techniques applied to it was released in 2013. And
which is when the Cybergram Challenge started. There wasn't much time for adoption and improvement.
And so 2015, the Cybergram Challenge was already over. So at the time, that was the newest thing. It had just come out, and people hadn't figured out how to apply it to all of these other software pieces of software at the time that communicate over the network or use encrypted communication or talk to file systems or whatever. Like, at the time, it was all just, here's some data, do something with it, give me something back. And I think if you view it through that lens, it makes perfect sense that the competition kind of reflected that, because that was what people thought these techniques were built to do. And like that was the extent of what people thought was reasonable. It took years of research after that to figure out how to apply them to everything else, right? Today, people are fuzzing drones in swarm algorithms of like, how do they interact with there's so much more that people do, but at the time that really wasn't there. I
think there's also a big piece here that's missing, which is that the CGC was entirely binaries. They didn't have the source code that we have for AICC, right? The tools
so your competition is easier.
Yeah, sure. You can tell yourself that. That's great. But no, I think that this also significantly scopes the problem. It's very, very difficult to run tools on binaries just as they are, and then to try and do this blindly for any generic binary, you have to scope the problem somehow, I think.
Yeah, I mean, I
great.
think another part that comes into it that comes from the binary part, but that also kind of influenced part of the decision is, one thing that I really liked about the AICC is, in the AICC, the problem is very straightforward, right? You try to find bugs, and then you try to patch the bugs in the source code. Those are like the two main thrusts of what you're trying to do in AICC. In the Cyber Grand Challenge, it was orchestrated a lot more like a CTF. You had to not only find the bug, you also had to exploit it and figure out how to abuse parts of the program's functionality to get you what else you wanted, on top of then trying to find ways of automatically mitigating it without being able to recompile the software, without being able to just, fix the code, right? That wasn't, at the time, that wasn't even anything anyone considered reasonably feasible, but it also wasn't part of the goal. And so there was this entire other aspect of automatic exploit generation, automatic mitigation without having access to the source code. And so I think there was a lot of focus on parts of the competition that weren't just the program analysis part of bug finding itself.
Yeah, which makes sense. And I think at least the vision of the AI Cyber Challenge of like, hey, we want to build systems that can help average developers and companies fix their bugs in their software, right? I think that was a big innovation.
And your typical developer doesn't care that someone could use this bug to do X, Y, and Z in an exploit. They care that there's a bug that could be used potentially in an exploit to do something. Let's fix it. And here's the fix, in fact.
And they want it fixed, exactly. That's what I was going to say. Yeah, 100%.
I mean, or the famous Linus quote of security bug is just a bug, right? Like they don't even care that it is a security bug. They just care that it's a bug.
Yeah, great. Okay, so now that we've set the stage for the competition, now I want to focus more on Team Shellfish and what your guys' approach has been to the AI Cyber Challenge. So this has been to recap, 2-year endeavor with the first year focus on qualifying one of the top 7 teams, and the second year really going whole hog 100% towards finals. So let's start with the team. So let's say, Lucas, we'll start with you. Tell us about the Team Shellfish playing like in and competing in and maybe describe your shirt. I think we'll start there. I should have started with the team name maybe.
Yeah, so I mean as the shirts say, we have decided to term the system that we built, our cyber reasoning system, artificial. With the obvious part being left out that we're intelligent, so therefore it must be artificial intelligence. But I think as a team, Shellfish kind of started as, it really was a relatively small circle of us where we were just like, should we do this? Should we do this? What if we did this? What if we spent the entire 2 years doing it? And then it kind of grew out, right? Shellfish is a pretty big CTF team, always has been. It's been pretty inclusive. When people want to join, we have friends in other clubs that want to join. They play with us. We have different universities all collaborating together. So relatively open team. And so when we started, we kind of approached it from the same thing of like, hey, we have universities that are all interested with interested students that all want to play. Let's just do it together, right? Let's do it as the Team Shellfish instead of as the university. And we started out with, at the beginning, there wasn't that much information available about the game, right? It took until about, I think, December when we first got the first document of like, what are we actually trying to expect? Because the challenge had just been announced. But we didn't want to be left behind, so we started immediately. So I remember, I think in October, we had our first hackathon, or maybe it was beginning of November, where we all met up and we were like, okay, let's imagine what this competition will look like.
Real quick, you're talking about November 2023.
Yes.
Mm-hmm. Or October 22. Yeah.
Yes. And we were like, we don't know yet what they're going to do, but we've been running CTFs for years as a team, right? So we have some idea of the decisions we would make if we were to host it. So let's just build for the competition that we would run if we were the organizers. And we kind of started. We had challenges that we had from CTFs, from other DARPA engagements that we'd worked on, from other research opportunities, right? We had challenges that we knew were difficult, and we just picked those and we decided, okay, let's build a system that can solve those. And then we just kind of decided to start building from there. And I think one thing that we've already mentioned last time, so I'm not going to go super in depth, but just for anyone that didn't see the last one, is became pretty quickly clear after the first document was released was we'd underestimated what we thought they were going to ask us to do. Or maybe they overestimated the difficulty of the thing they gave us. We'll leave that up in the air, right? But the very first thing they gave us was the Linux kernel, and we were very much floored by that because that was not what we had expected, right? That was not anywhere near the scale of software that we'd built our system for. The challenges we were testing had a couple thousand lines of code. The Linux kernel has millions. The challenges we were testing were in style a lot more similar to the CGC style challenges with relatively limited interaction. The kernel has infinite ways of interacting with in some ways. And so I remember the second hackathon, everything had changed, right? We started building all of this tooling specifically for the Linux kernel because we were like, okay, well, the Linux kernel is a big piece of software. We know how to deal with it. There's existing tools. So we started building all of that stuff. And then they released Jenkins, and now it was a giant Java application with, again, super large amount of code. But now it's Java. Now it's an entirely different system yet again. And in classic rabbit chasing the turtle fashion, we're like, okay, well, let's build something custom for Jenkins, right? And so that was kind of, I think, the end of our trying to build custom things. At that point, we were like, okay, clearly this isn't working, right? Like, clearly they're going to keep throwing new things at us. And the techniques we had tried hadn't generalized to the extent that we wanted to. And so I think then we kind of had this shift of like, probably like February-ish, February or March, where we're like, okay, screw this custom building. Let's just try to do a baseline of tools that can work. And that's when we started to look at more of these LLMs because they tend to, it doesn't really matter what code you show them, right? It's just a text interface that you feed text to. And so that was the first one where we're like, hey, this is actually kind of cool because this allows us to generalize some components that we couldn't previously.
So in terms of like a soundbite, you're saying that for the first 3 or 4 months of the AI cyber challenge, Shellfish ignored the AI part.
Oh, absolutely. To be fair, partially intentionally. Because we very much did like the kitchen think of like, hey, we know what works, right? We've done research in cybersecurity and program analysis for a long time. We know the traditional techniques that work. So obviously the first thing we put in was everything that we know works already. So AFL, Jazzer, right? Like our traditional fuzzers, syscaller at the time for the Linux kernel. We just put in the things that we know worked already because A, me included, some of our team members were still pretty skeptical of the capability of these LLMs. But also B, because we just didn't think they were necessary, right?
And rightfully so at that point in time. Yeah. We're talking 2023, right?
Yeah.
Yeah, I mean, we at the very beginning, we did have like, I think maybe 2 or 3 LLM components. One, of course, being patching. That's just a difficult thing to solve without LLMs. But then the other, we had a very rudimentary ask them, hey, is this code vulnerable? And we would feed it like entire files. And right when we were thinking on the scale of these thousands of lines of projects, we could feed a file or 2 in. It would cost a couple cents. But then when they give us the Linux kernel, recalculated because it was going to cost something like $10,000 to do the whole thing. And for reference, the semifinals had the restriction of spending $100 per challenge in terms of LLM credits.
There you go. Yeah, great. Yeah. Okay. So you had this big LLM credit, but now, okay, before we get too deep into because I want to get into like the architecture of the system and how you approached it. Like, Will, how many people were on the Shellfish AIxCC team? You don't have to give like exact numbers, but I think people at home want to understand like how many people were working on this, right?
Yeah, I think we had about 12 core people working at any given time, maybe 16, and then about another 10 that rotated on and off.
What do you mean
Depending
12
on
to 16 core at any time? Like you go
no,
into
so
Discord and there's like 16 people hacking away at one time?
yeah,
or-
exactly. No, we were all in a live call the entire time for 2 straight years. No, we had 12 to 16 people. It was probably 16. Full time, we were engaged in trying to make Artificial, our CRS, working, 12, 16-hour days sometimes just to make it to the finish line. And then, of course, as part of a university and larger team, we had 10 or so other people that, due to scheduling conflicts or availability, what have you, were able to donate some of their time as well to help with the effort.
Cool. Perfect. Awesome. Okay, so then, Lucas, back to, you talked about components.
Mm-hmm.
What does that mean? And
Yeah, list them all right now, Lucas. All,
No, that
all
is not what I
40 or
meant.
something of them.
this is, of course, a leading question because
Yeah.
I know kind of some of the answers.
Yes.
But talk about, like, when you talk about that, and maybe this gets into, you had this crazy team of people rotating in and out. So how did you approach the development of this complex cyber reasoning system?
Yeah. So, I mean, when you start out something like this, right, there's kind of generally 2 styles that people can do, which is one is you build one system as a whole that is just trying to do as many of these tasks as well coordinated as possible. Everything is linked together, maybe they just write into the same directories and everyone's trying to pull out from the same thing. And
Jan lit up.
Everything
He heard the visions of FSDB, and
He's
he lit
seen
up.
the horrors.
File system was invented for a reason, guys.
Yes, to store
People died
files,
to bring us
not
the
to
file
store
system.
a database. Entire fields were created around databases, man. Theory and practice.
No one uses that stuff in real life, man. But
But
everyone
even
uses
in the
file system.
database setting, right? Even in the database setting, you would have one centralized thing that has everything that everyone relies on. Everyone interacts with this, and it's very interlinked way of developing.
Like a hub and spoke model, right? If you think about
Yeah.
for people at home, like a bicycle wheel, right? You have the database or central component in the middle, and everything else is kind of reliant on that.
Yeah, or maybe 2 databases, right? Maybe you have something, but there's some central components that link everything together, and there are some central pieces of software that, and some interfaces between them that everyone kind of agrees on. And that's one way of building a system. It is generally probably something that I would have said we build as well if we had been a smaller team, right? But especially as a large team that is physically separated in 3 different universities, right? Arizona, California, and Indiana, right? There's a vast physical distance, and people that rotate in, right? As we were saying, people that come in for 3 months and then leave again. If you try to build the system, then everyone that is trying to contribute to the system has to understand every other part of the system and has to be able to interact with every other part of the system to be able to do anything. And so that works if you have a small team. If there's 3 people, that might be an architecture you go for. But especially for us with PhD students that all want to kind of work on their own thing, we kind of pretty quickly decided on doing a more decentralized approach where you have components that are more loosely linked, right? Each component just has one job. You take some data, you produce some output, and then that's it. And obviously this is a simpler model for every individual person to work on, but then it requires a lot of orchestration of getting that data from point A to point B, making sure that if I'm trying to do a patch and I just have the vulnerability finally available, then I need to start the patcher and all of this stuff. And so you have to have an orchestration framework that is able to do this and on-demand schedule tasks, on-demand feed data from A to B in a data agnostic way, because the idea is a new component can arrive tomorrow and the system can still handle it just as well, and nothing needs to change in the underlying system. And that method of doing it obviously requires us to build that orchestration framework, but it also requires a lot of that orchestration framework to be very abstract, agnostic, and be able to deal with arbitrary pieces of data But it has the advantage that we can all work on our own little things without breaking everything else and without having to understand everything else. And so those individual things is what we generally call components that are just like single job, take some data, do some analysis, produce some new data that gets picked up by someone else. And that's kind of how our system is orchestrated.
Awesome. All right. So then, Will, I've given you enough time. Maybe you know this is coming. How many components did the final artificial submission have?
Too many.
We counted, I think I counted, and it was about 65.
65? Like I wasn't
65 little scripts sparing. Some just were straight data pass-throughs. Others were very complex, like mechanisms for understanding the code. But in total, if you were to look at the little blips on the graph, on the data flow graph, every node, there was, I believe, 65.
Which is something super interesting that we didn't mention, but because you basically had this, you're describing what we called the pipeline of the system with components and how data flowed in and out, you could create this graph and actually watch the system operate in real time. Yeah. So as nodes had data available for input, they would then get started as jobs, and then they would produce output that would start other jobs.
It also creates, sorry to talk over you, Adam, it also creates this fascinating effect where, as Lucas said, people like to work on their own component. Right on the kind of semifinal day, of course, the professor showed up for the very end and to just mog around and chill out. But I was working on like one specific component. I had no idea there were 65. This is insane. I remember I ran a line counter on the whole repo, and I was just blown away at the amount of lines in there.
Wait, how?
Like,
what do you remember offhand? What that number was?
270,000 lines of Python, plus other
and
stuff.
Bash.
And Bash.
And
Bash.
And
Bash
and
some
YAML
significant amount of Bash. Yeah, templated Bash.
Just to let the folks at home know, Lucas and I learned an incredible amount about software management and foundational like development techniques, and applied none of these.
Of course.
Well, because you learned it while doing it, right? So if you think about like where you were 2 years ago, you guys have, I know, been involved in open source software. You've developed software, you've released it, but managing a team of, let's say, even 12 core people with 10 additional ephemeral people is a completely different beast.
Yeah, especially when everybody has their own wants and needs and
are you saying these are people? They have wants and needs?
I mean, I try not to think of them as people. It helps me sleep better.
They are labor.
Yeah, exactly.
They're a shellfish unit of work.
But exactly. In true shellfish fashion, instead of going with a pre-designed, some sort of orchestration framework, we just rolled our own. It's an insane monolith made by Audrey Relmont that's been open source this whole time, by the way. Anybody at home could have decided to pick this up and make their own CRS as well.
Partially.
Yeah, in case you could trick another team into using your infrastructure.
I wouldn't wish that on them. I really wouldn't.
So after we open sourced our cyber reasoning system for the Cyber Grand Challenge, we had this was 10 years ago. It was the only open source cyber reasoning system at the time. There were a number of other competitions of fully autonomous hacking around the world, and people kept using the mechanical fish, our cyber reasoning system, in these competitions because it was open source. And every time someone would email me like, "Hey, I stood up the mechanical fish," and blah, 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 and I'm like, "Oh my god,
you poor soul."
People won crazy amounts of money basing their cyber reasoning system on our cyber reasoning. It was really cool to see, but like, it was painful for them.
And there are
the growing
other
pains.
requirements that we didn't talk about, right? So at least in the finals, you could use tons of cluster compute, and you had access to, what was it, an Azure environment to spin up your machines because you had this much greater budget than $100. But at the same time, you needed people not only to be able to dev their individual components on their machine, but also dev their component as part of the pipeline using real inputs from tests. And so you needed them to be able to run the pipeline also locally. And even, I think some of us were running the whole system just on one machine.
A little bit beefier machines are required these days, but yeah.
Well, 64 components running, you need, and some of those are fuzzers. That's the
For semis, I was able to run it on my laptop at one point of like 12 cores, which was pretty good. That no longer possible, but
I mean, one thing that I will point out is that is kind of cool about it too is I mean, I think twofold is one, if you ask Jan right now, right, like what was the structure of the mechanical fish? I think it was a lot more of the former of the kind of system where you had one database. I remember because it was called MISA, I think. And you had one fuzzing thing, and then that was trying to communicate with the other things, but there wasn't, I think it was in total maybe like 8 components, something like that. I think it was.
Yeah, well, let's say 16 or less.
Yeah.
Probably closer to 10.
Yeah. And so our system has grown a lot beyond that. And the other thing that was cool about this, though, is because we had done this early, right, we had always designed the system to work like this. And we had designed it to be able to run on 12 cores as well as in CI on 96 cores. I think we had a lot better of a start into the post-semifinals round, where now you're running in a cluster, you have way more resources, you have you can spin up variable number of fuzzers, you can auto-scale to whatever degree. That was a lot easier for us because our system was always designed with that in mind, because we needed to test it locally. But in the game, we had way more resources already.
Can you give us an example of that scaling factor? Like what's possible?
Yeah, I mean, I think currently right now, I don't think there's even with the system in finals where we had over the 10 days, I think $50,000 of Azure compute. That buys you like thousands of cores of fuzzers.
It was 85,000.
85.
Yeah, it was a lot of money.
That's where that 3 milli went. Well, part of it, and the other one went to an AI provider we'll talk about in a bit.
But yeah, I think we had per target with 8 consecutive or 10 consecutive targets. I think we had like 1,000 cores per target of fuzzers that automatically dynamically spin up. And the nice thing is our system, when there is no challenge available, also automatically spins them back down, right? So we're not wasting money while we're not using it. If it turns out we ended up disabling some of this for resilience, but we could orchestrate the system in such a way that if we have a single target, that single target can take all 8,000 cores of fuzzing and do something with that.
And of course, maybe to Jan's chagrin, as more components spin up that need the resources, the fuzzers will spin down to accommodate the amount that needs to be spun up.
So that the reason it's to my chagrin is early on in the AICC, based on lessons learned in the Cyber Grand Challenge and the complexity of our dynamic allocation and our infrastructure in the mechanical fish, I pushed very hard for static allocations. We're going to fuzz on X cores and patch on Y cores and etc.
No, but I think your advice was more almost high level than that. It was simplicity. You said build a simple system, and
exactly.
that is part of that.
That's not what we did.
Hey,
and I knew you wouldn't.
Every child doesn't listen to their parents and has to learn the same lessons. It's just the same goes with PhD students and advisors, and the same apparently goes with hacking teams in DARPA cyber challenges. Okay, great. So then can you give the people at home like the high level bird's eye view of the pipeline? Let's go Lucas, if you can give us like the what. So target comes in, what is a target at a high level? Let's not get into all the minutia, but like what is a target and what happened to it through the pipeline?
Yeah, so maybe for quick context in terms of the what is a target, one thing that changed from semifinals is the organizers standardized on the OSS-Fuzz framework as a method of what should a target look like. And if you don't know what OSS-Fuzz is, OSS-Fuzz is a service by Google that allows open source maintainers to add their own pieces of software that could be as simple as writing a little Docker file that allows you to say, here's how I can build my target. and a little script together with a description that says, hey, where's the repository where if this giant system that Google has built finds bugs, where can they report them to me, right? And so as part of that, they've built this interface of like, how do we make arbitrary pieces of software available for analysis? And it requires a little bit of work by the maintainer, right? They have to write a Docker file. They have to write a script that tells the infrastructure, here's how you can build me. And Google has made this available, and I think it at this point has about 1,500 pieces of open source software that have been integrated into this framework. And so when this target comes to us, really what it comes is as 2 parts, optionally 3 depending on the type of challenge. The first one being just one archive of all of the source code of that application, right? You can think of this as just the Git repository taken, cloned, and packaged up into a file.
Boom, here's the code, find me bugs and patch them.
Exactly. And then the second part is that OSS fuzz integration wrapper, which is that build script and the Docker file and the metadata. Optionally, there's a third component for a challenge in the AICC, which is of type Delta mode, where they give you a diff and they say, hey, when you apply these changes to the open source software, there's bugs, find me bugs in the now newly changed piece of software. But in that version, only report ones that were introduced by this change. Like, don't report ones if they were in the original code. We only care about what has been newly introduced. So that's generally what the challenges are. They're either full mode or Delta mode, and they come as these packaged pieces of source code. When they enter our pipeline, the very first thing that happens, and that happens in OSS fuzz as well, is obviously we have to build the software a bunch of time. We have to...
Maybe not obviously. If you were taking a pure AI-based approach.
That's fair.
Maybe pure source code analysis in AI, you don't actually need to build it.
You know, yeah. Lucas, we never asked the AI how we should build the software.
You never asked whether you should build the software.
Well, okay, so one thing is, as part of the game, the things, this is probably important to mention, the things that we can submit to the organizers are mainly twofold, which is one, we can give them a piece of data and say, if you feed this piece of data to this software, to this specific entry point in the software, it will crash, right? And so what then happens on the organizer side is they run that piece of software, feed the data in, and check, well, did it crash, right? And if it does, then they give you vulnerability scoring points. The second thing we can report as a system to the organizers is a patch where we say, okay, if you apply these additional changes to the software and then run that same crashing input that you gave me previously, does it still crash? If the answer is no, then you patched the vulnerability to some extent. And there's some additional tests that they that they run to make sure you're not like trying to game the system. They check their own patches against, and so there's some scoring logic there, but that's kind of like the two things that your system reports is bugs in the form of a crashing input and patches in the form of a change that needs to be applied to the system. And so obviously you might want to replicate this locally in order to make sure that the thing you're about to submit is actually valid. And so generally the first step is like the building part of the pipeline. And our pipeline doesn't build the software just once, right? You don't just build it one time, you build it a bunch of different times for different purposes. So fuzzers need specific customizations to the software to be done so that you can fuzz more effectively. When you are trying to look at like, hey, which parts of the code has my input reached, has my analysis tools reached, you use coverage instrumentation. That comes with a specific set of changes to the compilation. And so we built the software a bunch of times, and then you can kind of, that's like the first layer of the pipeline. Then you have a layer of static analysis and like almost like understanding the software. So splitting it into different functions, trying to find out what functions are there, running existing vulnerability scanners for example, like semgrep and codekill, trying to find any known vulnerable patterns. Maybe this is a first analysis step of LLMs where you give them a bunch of functions and you just ask them, hey, are these vulnerable, right? Like purely by looking at the code, what can I determine of this software? And then that's kind of the second layer. Then the third layer starts, which is most of the dynamic analysis. So this can be traditional fuzzers. We generally have mostly 3 with some customizations. Jazzer for Java, AFL for C, and then libfuzzer for C. And as well as LLM components. Here we've now built a bunch of them where they try to actually like feed. We ask the LLM, hey, can you write me an input that will crash the software, right? Like here's a bug, here's a program location where I think there's a bug. Write me an input that tries to get there. Write me a grammar that tries to reach there, right? Like whatever you can come up with, like anything that produces inputs that we can actually test against the target software and say like, hey, perfect, this crashed, go forward. And then after this stage, you kind of come to the triaging part, I would call it, where now that you have a bunch of these results, you have a bunch of crashing inputs, you have crash reports of like, hey, these were the stack traces when it crashed, here's what the state looked like. Now you have to understand, what is the actual bug that we found? Is this the same one in 4 different ways? Are they different?
And this was important for kind of game reasons, but we won't get into too much depth. But it also, there's the game, but I also like to think of the real world impact of this stuff, right? So it's like, okay, but as a developer, you want to know that there is a bug. You don't want to know that I found 1,000 crashes and turns out they're actually all the same bug.
Yeah, and that's something that is very real. Like people are very annoyed if you just report them the same bug 10 times, right? Because it's a waste of their time.
Exactly.
The other part that this is important, though, is not just for the game reasons. It's not just for the real world part of it. It's also the better you can do this stage, the better you could understand what the actual bug that you've discovered is, the more information you can give to the last part of the pipeline, which is the actual patching and the actual patch generation, where we now use multiple different patching solutions, all based on LLMs in some way, shape, or form, just with different strategies of, hey, I have found
and very
this bug.
Smartly, I have to say, named Patcher and then a letter. It was absolutely insane.
Yeah. No, it makes all the sense in the world that we have Patcher Y, Patcher Q, and Patcher G, which isn't a Patcher, by the way.
Yes, so insanity.
And Patcher Y is smart.
You were thinking.
And Delta and Dumb and whatever, yeah.
Amazing. Okay, so then the patching component is at the end, or there are other components?
So it's near the end. So because once you get a patch, there is one more thing, which is, similar to the first step, you need to understand is this patch the same or similar to one I already have? But also you need to do a bunch of cross-checking of like, did it make the crash go away, right? This is part of the patches generally, but it's kind of this idea of like, you want to be sure that your patch is correct. So the last part I would say is like a separate step of the pipeline is we have some fuzzing, for example, on the patches where we just try a little bit to try to get around the patches and make sure that they're not easily bypassable. And that's kind of like the linear progression of the pipeline. And then there's one layer above, which is the gameplay axis of the pipeline, right? Where you now have all of these results. Now you need to decide, okay, which ones of them do I submit in what order? And do I want to submit them? Am I confident? That kind of
And
other
deciding this strategy took, I think, 10 of binary and program analysis top scientists 4 or 5 days.
Hey, we also had some game theory people, at least 2.
At least 2 game theory people. Yeah, but we made a strategy in the end.
And even after that, it's still the scariest part of the system.
Yeah, which
By
makes sense,
far.
right? You're talking about, I like that notion of like it at the top layer or the bottom, right? Because the system is doing all this analysis, but you need to communicate those results and actually play the game in some sense, because it's not just you're not just creating this stuff. So you have to play the game. And so if you end up not being able to play the game, or you hit the wrong button, or you keep doing something over and over again, that would be a problem. That would be
Or that
very bad.
change you
Yeah,
made an
that's-
hour before the deadline turns out to be to be not so good.
Exactly.
Yeah, I think that was the scariest part for sure, which is we made all this cool stuff, and to us, obviously, this we did something really awesome. But if in the strategy or in the game we can't actually show, we don't submit anything for whatever reason, or there's some failure, and just even if we make it internally, but it doesn't make it out externally, then it doesn't count for anything.
Exactly, which is great. Okay, so Will, then, so we know the scariest component or the scariest phase. What is the craziest, wildest component, in your opinion, that exists in the system? And describe to us like what it does and why it's crazy.
Okay, I may have to give you two.
I only said one.
Yeah, I understand what you
I'm
said,
just
but I don't
kidding. You're
follow
just like an
directions very
LLM. You
well.
can't follow instructions.
Yeah. So one I think is our serif component, and I think it's crazy. One thing Lucas had mentioned that maybe we can get 3 inputs from the orgs. This extra third input can sometimes be the serif report, which for those who don't know is just a way of representing like static tool findings of, hey, there's a vulnerability here, and our job is to say whether or not there's a vulnerability. And instead of making impressive tooling or maybe some really cool
One sec, Will. You just
information
said
analysis.
you just said the organizers tell you there's a vulnerability. Why would they need you to tell them if there's a vulnerability?
Now you're getting to the crux of the problem. The organizers say a lot of things, but in this instance, they want us to verify what they had said. They give us an assessment that says, "Hey, there's a vulnerability here," and our job is to say, "Yes, that's the correct assessment," or "No, that's an incorrect assessment." And then
Why do you think they do this? Why would anyone care about this capability in the real world?
so the best guess, there's a whole meta component to all of this, but essentially the things that you need to understand at the core is there's a vulnerability that exists. We want to patch this vulnerability, and maybe there's a report of this vulnerability. And if you combine all of these 3 features, all of a sudden you start to kind of think a little bit of, hey, this maybe actually sounds like an issue that maybe somebody could open on a GitHub repo. That maybe somebody's found a bug, or maybe somebody's found a vulnerability, or maybe there's some CWE that comes in that says, hey, there's
Or
a
maybe
bug here.
Or maybe they just found code that looks suspicious, right? Like they might not understand entirely.
So you're saying
they
these
might
serif
just
reports
think,
might be mistakes
yes.
made
think
by an analysis tool.
Exactly, because it comes into, if that's a static analysis report, fundamentally, it hasn't executed the code. We don't actually know that there is a bug there. The tool says I think there's a bug here, but we know false positives exist in static analysis tools, and so it may be lying or maybe incorrect. Or I think the proper way is thinking about it is it's over approximating the program's behavior, and it's envisioned a potential vulnerability that doesn't actually exist.
So, Will, go ahead. Sorry, I
So
interrupted you.
back
You're
to
talking
the
about
back to the crazy. This component is crazy just because we decided to go with it, which is just ask the LLM. Just don't do anything complicated. Don't burden your brain. Don't use any CPU cores. Just ask the LLM. Is there a bug here? And it turns out that it works quite well, at least given the format that we've seen from the organizers and stuff we've generated ourselves. Is you have a relatively high true positive rate of whatever of assessing correctly or incorrectly.
So 65 components or 64 components are all devoted to finding vulnerabilities and patches, but you have just one component that just says, yo, is this report accurate?
I just need a yes or a no.
Just
man.
trust me.
Just trust him. Just trust him. That's all I need. But the real answer to the craziest component has to be Lucas's grammar guy. I don't think I've seen anything eat money faster. I've never physically felt myself get lighter as my pockets empty. When Grammar Guy is active.
Great. So what is Grammar Guy? So this is great. So you can tell us like what are the inputs to Grammar Guy, what are the outputs, and what did that component do?
Yeah. So of course, the underlying challenge to AICC is, where is the bug? You can have the best patching in the world, you can have the best serif detection in the world. If you don't have a bug to prove that these things exist, then you really don't have much. So we developed essentially all of our, or much of our bug finding capabilities on fuzzing. And on top of this fuzzing, we can't just have plain old AFL or libfuzzer, because although these things do work in practice, OSSFuzz has been using libfuzzer for years and years, and the bugs that it finds maybe occasionally, and maybe every couple months, it doesn't progress very much very fast. So Lucas had a brilliant idea, which is, let's mutate the input seeds that we can give to AFL. What if we could make these seeds inputs smarter, right? So we have the source code. We have great information like code quill queries. We have great information if there's a diff of, hey, this is code that's changed. So let's try and generate grammars that drill deeper and deeper into the program as we find more and more coverage, and come up with these as fast and as broad as we can. And that's really the money eater issue there, is as fast and as broad as you can, because although it's been incredibly effective, it's found bug. Without it, our bug finding capabilities maybe 75 or 25% of what it could be. But it uses like 90% of our budget.
55, excuse you.
Well, 55.
Of the LLM budget, you're saying?
Yes.
But the soul, it uses 90%. Anyways.
And is this because it's not good, or the LLMs aren't good, or because you need something different? Like, what's the core root cause of why it takes so much LLM time or budget?
I mean, I think there's so I think there's two parts just beforehand. I think there's I can't take all the credit for spending all of our money, right? Grammar fuzzing is an idea that has been around for a long time, and it was kind of a natural one to try to apply LLMs to, because it has been traditionally something that has required humans, right? Humans would go in and say, okay, here's the application. Let me understand how the format looks. Let me understand what inputs it expects. And then they would write a specification of like, okay, the first thing is a integer number from 0 to 10. And then it is followed by a string, blah, 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 right? And so this is a traditionally very human task of like writing these grammars in order to make the fuzzer better at exploring the state space, because it no longer has to consider the first thing being a number 11, right? Like it very much prunes the search space. And so this is a pretty old idea. But the LLMs kind of allow us to take that human part and replicate it with something that might not be as good as a human, but can do it a lot longer, a lot more often, a lot faster than humans can. And we actually had this already in semifinals. One of the interns at UCSB, Sebastian, has been working on that for a long time, and built the initial idea of like, okay, we don't trust these LLMs that much. We don't know how good they are. Let's break down the task and make it simple. And that is something that kind of you can see in all of our pipeline. A lot of the older components had a lot less trust in the LLM, right? They trusted a lot less in the abilities of the LLM to decide itself what to do. And instead really try to railroad the LLM into like, here's your task, you have one job, just do that one thing, and then the rest of the system would be built into the components. And we had that initial grammar guy, but one thing that we tried after that was, you know, in between semifinals and finals, as these models got better and as they acquired more ability to, for example, call out to external tools and retrieve additional information, one of the things that I think the initial version of the grammar agent that ended up spending so much money initially was written in a day or two. That really is just a couple tool calls allowing the LLM to collect coverage, and then trying out this grammar, producing a bunch of inputs, seeing what coverage they hit, and then asking it, okay, now do better, right? Build a better grammar. And as part of this, as the LLM explores the code, it has the ability to look at functions, it can look at files, it can grep through the source code. Whatever tool calls you make available to it, as it does so, it accumulates context and it accumulates knowledge within the interaction of like, here's stuff I've already tried, here is grammars that have worked, here's mistakes I made. And in that version, it just accumulates context infinitely. Obviously, there is a boundary imposed by the LLM, at which point we have to, prune it and truncate it. But really, the idea was just let it have everything it's ever seen and see what it does.
Yeah, after about 10 calls, you hit that context window pretty goddamn fast. But I mean, something else here. Grammar Guy could, well, one of the reasons it's insane is that we had to base our budgets for this final allocation based on the fact that we are physically limited by the rate limit in which we can send Anthropic tokens, for which Grammar Guy is sending them. And so we had to literally split off less and allocate more money to OpenAI because we physically would not have been able to spend the money in the time frame.
So maybe we can kind of pull on this thread a bit with this question. Favorite AI?
Ooh, I like it.
Yeah. I think Anthropic for both of us.
Daily driver usage or coding or
for
in
for
your
coding
system
for sure. Well, so there's an interesting thing here, which is I actually think OpenAI is great for maybe like more nebulous tasks or things that require decision or critique. But if you're asking to generate code, if you're asking for decisions to be made on code that are minute or specific, then I think Anthropic takes the cake for pretty much any use case that we have.
Yeah,
great.
I think one more thing is like I think this is again kind of that shift, but I think Anthropic was the first ones to get there. I think now some of the other models have caught up. So I think like Gemini, for example, they've caught up exactly. Gemini is now pretty decent at it. We weren't able, due to rate limiting issues, to use it to the extent that we wanted to. But also some of the newer OpenAI models, I think they've also realized that this paradigm of like tool calling and being able to write code to do more things is just so much more powerful because it allows the LLM to think about less, and it just has to write some code that does the work for it, right? The same way that people were always harping on these LLMs about, they can't do math. Well, just give it a calculator, right? It doesn't have to be able to do math. It just needs to be able to say what it wants to be solved. As long as it can do that, the machinery that you build around it can do that hard work for it.
Yeah, that's cool. And it goes with what I observed when using Claude Code to try to implement some tests, which was my kind of contribution to the AICC push. And it would actually, I watched it, I told it to like either generate a test case to hit here or fix a test case or whatever. It would add debugging code into the system, run the test case, look at the debugging code, and then be like, oh, yeah, I see the problem. It's this. And then it would go back and delete it. That's like what was the crazy thing to me.
I mean, it's been very interesting to see these tools like progress over time from where we started in 2023. We've mentioned a couple times about how our whole paradigm has shifted, but like tool calling didn't exist, right? Tool calling was kind of like a fresh thing there. We built our own tool calling capabilities initially. Like I remember making our own like Python execution sandbox where we say, hey, can you generate some arbitrary code for us? And then we execute it and feed that back into the system. Now there's entire frameworks that allow you to build up the agents, and tool calling is almost a given with any model, minus a few. But it's been really interesting to see like the industry and everything mirror us in a way, or the things that like we've noticed lacks or wants that we had and made it and created them for ourselves. And then, other people obviously had also wanted these or needed these. And then they develop it kind of side by side, which was interesting.
Great. That's awesome. Okay. And so, yeah, I think kind of we're running towards the end, so we'll kind of close it out. So what's happening now? So all of the teams submitted at, what was it, June 26th? Was that the
Yeah,
deadline?
that was the morning
Yeah.
of June 26th, 8
Yeah,
a.m.
so a date that will live in some people's memories, but not ours. And so every team submitted on 26th, and the organizers are running all of the CRSs on all of the challenge problems, and we'll find out. Yeah, right now as we are recording this, they are running that. And so, okay, maybe a couple final questions. Predictions. Predict. How do you think Artificial is going to do in this competition?
So PR response, we're first place, right?
Of course.
Obviously. Real response, I think we're probably, I would say, second or third.
What do you think will be the differentiator?
I think that all the gaming, all the theory crafting, gaming, dedupe stuff, if you did deduplication correctly, is what makes you number one. I think that if you're able to accurately identify, hey, I found, these bugs and they're different out of 1,000 crashes, that puts you on number one. I think it's very easy to go all in of I only found one bug, or it's very easy to go all in the sense of I found 1,000 different bugs. But if you're able to differentiate even like 2 or 3 bugs, I think that's what actually puts you at number one.
Yeah, I agree with that. I think and this is not to sound, diluted or like grandiose or anything, but I think we've built an incredibly good system at solving the task. I think the only question remains of like, how well does that system play the game? And I'm sure there's some team that will find new bugs that we haven't. I'm also pretty sure we'll find bugs that other teams don't have. I think there's always wiggle room in the results, but I think what it comes down to, and I think the thing that I'm most scared of is that, something happens and their system melts down, or hopefully not, or we have bugs and we don't submit them, right? That would suck. But I think that notwithstanding, I think we have a pretty good system that we've built, and I'm pretty confident that we'll do well.
Awesome. So based on that prediction, what is, in very short, your secret sauce? What's like the Shellfish Artificial secret sauce?
I think we've said this in actually a couple different places, but the number one is,
please tell us again. We would really appreciate to hear it from you.
Yes, of course. Use LLMs, but they have to be grounded. Give you great output, very usable, but a lot of times it's not 100% correct or 100% the truth. Make sure that you have some way of verifying that what it gives you matches with reality, whether this is test cases, or maybe you're able to gather constraints from somewhere, or actually just run it. I think that being able to trust but verify is the number one key to success here.
The term that I came up with, I think, in the end for this is you have to baby-proof your code.
Mm-hmm.
From the LLM itself.
Yeah, as a parent of young children, I love that terminology.
And because you came up with it, so obviously.
Oh well, no. I think it was
Quick, Jan, come up with some
me.
80s video game that had the term in it.
That's right.
Incredible. Okay, and
actually, can I?
Oh yeah, go ahead, please, Lucas. Yep.
Yeah, so I wanted to follow up real quick because I have a little bit of a more concrete answer that I think might be cool, which is, I think one thing that I really like is I think it's very easy, in quotation marks, obviously, in terms of a 2-year research project, but I think building LLM components is the easy part in a sense, right? Like you have to make them work well, and that's what Will was trying to hint at. But one thing that I really like that our current system has is we've kind of approached it from 2 angles. We've approached it from the angles of making the LLM be able to better use the tools that we give it and make sure that it really is good at that. But the other thing that I think is really cool is we've tried to build traditional analysis systems that are based around what the LLMs are able to give us. So Will mentioned Grammar Guy as like this tool that writes grammars. Well, we've also then taken that idea and built a lot of software around the idea of, okay, this tool is able to give us grammars, let's try to use them in additional ways. So let's feed those grammars back to the original fuzzers to fuzz with those grammars instead of just let the LLM do stuff with them. Let's try to find ways of augmenting these grammars with additional information, where we are able to distill some of that idea of what the LLM was trying to do, right? So maybe we can detect the LLM was trying to create audio files. We might not know exactly what the LLM was trying to do, but we can use that pattern recognition ability and say, like, hey, this looks like an audio file. Let me try to automatically use these existing grammars that I have for audio files. And so I think this interplay back of like this LLM produces information and we use that to make our traditional analysis better is something that I think is very cool in our system that we didn't have before.
So this is super cool because basically we started, you might say you started with the traditional program analysis for the first couple of months. And then you started splashing in more and more and more AI. You can imagine a different approach from researchers that have more of an AI background, that start with the AI and maybe later on start splashing in more program analysis. Do you think that there'll be these two competing approaches, like in an overarching way in the AIxCC? Maybe 3 teams do one thing and 4 teams do another? Or do you think everyone is going to kind of end up with the same place regardless?
I don't think everyone's going to end up in the same place. I think there's a lot of difference in the shift in focus, right? I think there's almost certainly teams that invested more into these ideas of like, let's just make the LLM really good, right? Like, I think it's probably fair to say that might, other teams have done more in that direction of like trying to build different versions of these systems. I think the other direction of teams that have done more, maybe only rely on fuzzing, is possible, right? Like maybe someone decided to not use LLMs except for patching at all. I don't know. I would imagine not, because it's easy enough to at least do the minimum to get a little bit of an advantage. So I think there's room for that space to shine. But I think everyone will end up with some mix of the two. I can't imagine why you wouldn't, right?
Yeah, of course.
It's easy enough to mix these things together. I think there will be some two kind of groups, but there's not going to be as much disparity between them as these people went all in on one and these people went all in on the other. It's like these people just were more comfortable with doing this type of work rather than the other.
Which makes sense. So there's a selection or a forcing function of quals, right?
Mm-hmm.
Yeah, and the prediction basically, people probably will have started on maybe different parts of a side of that spectrum, but will meet somewhere toward the middle.
We'll see.
The CGC.
Go ahead.
For the CGC, I was shocked at how similar all of the final designs were of the cyber reasoning systems. Everyone had a fuzzer, a way to help the fuzzer get unstuck when it reached the parts it couldn't fuzz through, and a general patching engine. That was for the most part which was really interesting. All the minutia differed, but the high level approaches were similar. I'd be really interested. Maybe we should do another episode afterwards with all of the teams.
Yeah, one thing I'd be curious to see is if one thing where I can see a little bit of a gap in the spectrum is how much did teams try to do very vulnerability specific or target software specific things, right? So did teams try to build agents that are just really good at only buffer overflows but nothing else? That kind of an idea, where I think we fall on the end of we try to treat everything the same and we try to explore the code as evenly as possible, and we have some components that are specific to specific types of bugs. But I think that I'm more curious to see if did anyone go full in, like we have 30 different LLM agents, each one doing just one thing really well.
I really hope somebody went with the Skynet approach. We talked about doing this ourselves, but of having like our orchestration is very like input output driven. But I really think there's something to be said for an approach where you give the LLM control of, oh, I think this problem is better solved with static analysis. I think this problem is better solved if we slap on some fuzzing for a little bit. Oh, I found this interesting thing. let's actually use this other tool that I can do. If there's some some team that's super heavy into LLMs, I really hope they took some
really
approach
cool
like
to
that.
see.
That'd be awesome to see.
What about a single prompt? Develop a cyber reasoning system. Go.
Need more be
They're
said?
just like bootstraps.
Okay, final question, and then we'll let everyone go. Lucas and Will, if you, knowing what you know now, if you could change one thing about your approach to AICC, could be team-based, technical, whatever, what would you change? And you can also say, I would never have done this in the first place.
I definitely would have done it still.
Yeah. Well, you want to go first, or should I go first?
You go first, Ben, if you got an idea.
So, I'm going to give you a little bit of a cop-out answer, because I think at the end of the day, I wouldn't do anything different. Like, realistically, from the place we started at, this was the natural version for our team to go. And I think we kind of ended up where I expected we would go. Like, not necessarily with the same system, not with the same complexity, not with the same component, but I think it was always trending in that direction. I think if I had to start over now, in order to try something different, I would do the second thing that I just mentioned. I would try to go LLMs first, right? Try to just because I want to know what it would look like. So I really hope someone did it. Is like, do LLMs first, build LLM agents for everything, and build custom LLM agents that are really good at maybe even something that I'd heard a couple of times was this idea of like really infusing the LLM with as much personal information of how would I solve the task, and trying to follow the LLM, make the LLM follow what a human would do. I think that would be really cool to see, and I think I'd be very curious to see how far you can take that. I hope someone did, because everything is going to be open source at the end, so I can't wait to read the code.
Yeah, that's going to be great. So you would have you would have just done AICC like 4 times is what I heard, and just done different strategies.
Yeah.
Okay,
He
awesome.
just wants to be every team himself.
Cool.
And
He's got a
figure it
point.
out. Yeah.
The system feels very Shellfish. It was very cool. It's anyways.
I think I imagine it would be difficult for us to really do anything differently, given like how technology kind of ramped up over time. I think maybe increased adoption of like LLM as time went on, because I think we really had kind of like a sticking point of pre-quals, after quals of like, oh, we're only using LLMs a little bit, to, oh, let's use LLMs for everything that we actually like think is good. But beyond that, there's one singular thing I would change, and it is use a monorepo from the beginning. I think submodules are a curse. They are the spawn of Satan. They have bitten us in every which way that is possible to be bitten by submodules. If we had a monorepo from the very beginning, then I think we could have legitimately saved like 10% of dev time in quals.
Vindicated. When Jan was saying keep things simple, I said use a monorepo.
Yeah.
Yeah, I think
real quick.
Kids need to learn their mistakes.
I agree.
I know Adam said last question, but like one more question. You said second place for guaranteed. Boom. Maybe first. So second place, what are you going to do with those 3 million?
3 million? First, take a break. It's been a long 2 years. And then make some more cool stuff, man.
Team vacation to the moon. Can we go do that for
Mars.
3 mil?
We could probably send a couple of us for 3 mil.
Nice.
That costs way more money than I think.
I
think
know
we just
how much...
pay for the LLM to write all of our papers going into the next 20 years. You just buy LLM credits to do all of our research, so we don't have to do anything. Because
hey, that'll save me a lot of money on PhD students.
Exactly.
In this economy?
Awesome. All right. Well, thank you, Lucas and Will, for joining us. We're super happy to have you today. I'm Adam D. You can find me online at Adam Dupay. He's Zardus. You can find him online at Zardus. Together, we are CTF Radio, and you can find us online on YouTube or Twitter or /X at CTF Radiooo. You can send us questions through email at ctfradioo@gmail.com. And you know what? We may just use your questions on a future episode of CTF Radio. I think from what I've seen here, we didn't even get into, there's like so much craziness we could have got into about the stuff that Jan got up to during the final push, the almost lack of actually submitting anything. So there's so much stuff we could have got into that we didn't, that maybe we'll have to have another episode, but that'll either be a happy or sad one, depending on what place we get. But anyways, if you have questions for Lucas and Will, feel free to send them to us. We'll be happy to do that. So take care, everyone, and happy hacking.
Yeah. Thanks, guys.